So we have 3 Tesla MRI, which is what I already said, quite special for an institute like ours. Here, patients with anesthesia, difficult, not collaborating or not cooperative patients who have anesthesia or children or whatever. And we have the room, of course, here for that. And, normally we are using this type of cap. So this is a cap just with the electrode cables, and this is just copper wires. So we take everything into the scanner. So you have to be a bit careful, of course. So it is twisted wires, and we have these current limiting resistors, 10 kiloohms, in order if there are currents, induced currents because of high voltages, then there is heat dissipation here, so that there is no burning of the skin. So we take all the precautions to preserve the safety of the patient. Yeah. So this is what we take into the scanner, and this is the system that we are using for the acquisition. That's of course outside of the scanner. Yeah. But the system is connected to the amplifier, and the amplifier is taken into the scanner, and also the pulse oximetry meter and everything we developed ourselves is taken into the scanner. Yeah, together with the patient, and of course only trained personnel may do the EEG fMRI experiments. There should always be a physicist, that's what I say, or a biomedical engineer available at the moment that the measurements are done. And this is what we are measuring, so a lot of artifacts when the EEG is recorded in the scanner. So now we go to the next presentation or demonstration. That's why we have these special caps, such that we can remove the artifacts.
As we heard already in the afternoon from Pauli, here in this institute patients are investigated for epilepsy. So what is essentially done is that people are lying in the MRI scanner while they are out of medication for epilepsy, and at the same time EEG is recorded in order to detect epileptical spikes. And with this EEG data, it is then tried to calculate the epileptic focus in the brain. For that, of course, the clean EEG data is necessary. In former times, the off-the-shelf EEG has been used, which are basically only MRI-compatible electrodes, and in this project we developed improvement of this technology. So we constructed this reference layer electrode cap, which consists additionally to the EEG electrodes of a reference layer that is recorded in addition. This is just an outline of the layout of the cap. So it's according to the International 1020 system. We have 29 channels here. Actually, we have 30 channels, including the ground channel you see in the middle here. It's there. And we have 2 channels for ECG also. So ECG is measured on the back by using two one-way electrodes. So as we have the double amount of channels, we don't have only 60 channels. We have 60 channels instead of 30 channels. Sorry, one for the EEG and one for the reference. Each electrode is placed in a housing, which is symbolized here in this drawing. So the red part here, it's a little bit small, I'm sorry for that. The red part here is the EEG electrode that picks up the EEG of the patient. the signal then goes via a resistor to an interface box. In this housing, directly on the cap, there is an isolation through a PCB here, and on the other side of the PCB there is a second electrode, which only should pick up the interference of the scanner. And all those reference electrodes are interconnected by some cell line, which is filled into the tubes of the cap. So it is filled with conductive fluid.
No, why is that?
Because the reference layer should imitate a second skin, which behaves similar to the real skin, and the distribution of the induced artifacts should be very comparable to the skin itself. So also this is going through a resistor and to the interface box. At the interface box there is another resistor, and then at the end it is connected, the signals are connected to the amplifier. Here there is a micromet amplifier with 64 channels used. So we currently fill all the channels with our cap. This is an older image where we did the first prototype. So this is with a cap that was one version before that. We did measurements with a phantom for the heat and for the image quality. So this is the MRI image quality, let's say reference image, or this was the first image that made us continue to advance to more detailed experiments than with real brains, because this gave us the confidence that the images are usable. What we also did were temperature recordings. That's only, well, a very small subset of all the tests we should do with this cap, but that was more or less the minimum thing we could do, and we didn't see any tendency of the electrodes getting warmer during the fMRI scans, so also this made us confident in continuing to humans. And this was one of the first measurements with a volunteer. He was of course not a patient. And there we only measured alpha activity, so eyes open, eyes closed. And what we wanted to see here is whether there is some EEG signal after filtering using the reference layer, and we saw that there is the significant 10 Hz peak around. So that was the first part.
This part is a little bit more into data processing. This is an overview you also saw in the presentation of Pauli. And this is basically a summary of how the normal processing happens. On the top you see the signal which is acquired outside the scanner. In red you see, in blue you see the actual signal from the EEG, and in green you see the reference signal. And as you might expect, there is no actual signal because it's not inside the scanner. And this is visible in the second row, where you see huge artifacts when the patient is in the scanner. Because of the gradient fields, those cause the large deviations. Those can be corrected for. That's a sort of standard approach in the pre-processing step. And that's what you see in the third and fourth row, where the gradient artifacts are removed. And it also obtains a much clearer EEG. The problem is there are still some artifacts in there which are related to the individual pulses, for the individual slices of all the volumes. And those can also be corrected for. And for that, one of our PhDs has been working on a method involving singular value decomposition, which is able to correct for these pulses and obtain an even more cleaner EEG signal. So to give you a bit of an overview of a practical situation, because the results I showed you before are for a resting state. Of course, we have patients who have epilepsy, so they might have spikes in their EEG indicating small discharges. And this is an example from outside the scanner. There's one electrode which hasn't been connected properly, but if you look closely, point it out, you can see, for example, here, here and here, some discharges which indicate that there's a spike happening. And of course, outside the scanner, these can be identified relatively easily. The only problems arise when you, of course, put the patient inside the scanner. And on the left, you see the already gradient-corrected result. So that's the result you can obtain with the normal cap without any specific software or any special additions. And on the right, you see the version you can obtain when using this two-layer cap. And some additional processing. You can already see that's a much clearer, less noisy EEG. And what you see in green are the individual artifacts which are induced because of the pulse artifacts for the individual slices, which are less visible in the right side. And this is especially the case when you look at an entire field of EEG signals. So this is the gradient corrected, the standard off the shelf, so to say, version. And now also including the places where the volume artifacts normally occur. And you can clearly see that at the green annotated lines there's a discharge visible in almost all signals. And if you now switch to the corrected version, you can clearly see, I'll toggle a little bit, you see that there's a much cleaner result. And this is especially the case when you look at the discharges I mentioned before. That's why you want to use these signals. So on the left you see again the not pulse corrected but only gradient corrected version. On the right the special version, in which you can on the right clearly see the discharge, but in the left side it's almost invisible when comparing to the pulse artifacts in there. So that's basically how the results of this method look like. And of course at the end these results, these discharges, can be used for generating source localizations, finding the actual focal regions where the epilepsy happens. So that was basically the summary. Thank you.
And how do you know that you're not, when you do the pulse correction, that you're not actually correcting for a real epileptic event? How you do distinguish the two different?
Yeah, it requires annotations. Let me see. Over here, for example, that's why you place these green annotations. So you can obtain the actual signal that these pulses emit, and so you're sure you're not removing actual seizures. That's basically what ensures that.
Yeah, okay.